Welcome back to our isomer video series. So in this example, we are going to try to determine whether we have conformational, structural, or unrelated compounds. And remember, conformational isomers, those are just the same compound pictured in two different ways. So the first thing that we had to do was to find our longest carbon chain. Okay, so I'm going to go back to my highlighter, and I have to start at the end of a carbon chain. And actually, before we do that, let's go through and locate all those carbons, because sometimes that can be easier. Okay, and we'll do the same thing here. And we're actually going to find the molecular formula first. So if we want to find the molecular formula, we first want to count up the number of carbons. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons on that first one. And then on the second one, we've got 1, 2, 3, 4, 5, 6, 7, 8, and 9. So both have 9 carbons. Remember, they have to have the same molecular formula to even be considered isomers. Okay, now we need to check the number of hydrogens. So a quick trick is that if neither one of these are cyclical, and if they all contain nothing but single bonds, it's going to be guaranteed pretty much that they have the same number of hydrogens. But we can check this. So you may want to rewrite the structure and write it with it as a condensed. So we're going to rewrite the structure over here. Remember, every time that I have a carbon, let's see, we've got 1, 2, 3, 4, 5, 6, 7. So we're going to go 1, 2, 3, 4, 5, 6, 7. And then on the second to last, we've got a carbon coming up and one more. Okay, so each carbon always has to have 4 bonds. That carbon on the end only has 1 bond currently, so we're going to add 3 hydrogens. Carbon in the middle here has 2 bonds, so we're going to need 2 hydrogens. Carbon here, again 2 bonds, so it needs 2 hydrogens. Again 2 hydrogens. And then this carbon already has 3 bonds, so it only needs 1 hydrogen. And then again 2 hydrogens and 3 on these end carbons. Okay, and if you add up all those hydrogens, you should get H20. And now I'll let you try that with the second compound, but just write it out and add in all those hydrogens, and again, you should find that it's C9H20. So we do know that it's some type of an isomer, and we've got to decide if it's conformational or if it's structural. So here's where we're going to pick up our highlighter, and we're going to find the longest carbon chain. So if I start on this end, and I go across, when I get to this fork in the road, I have to decide which way to go. I want to go whichever way is going to be the longest path. So I'm going to continue up in that direction. Okay, and then when I number the carbons, I'm going to number them, since I don't have a functional group, I want to number them to go closest to the methyl group. Okay, so even though that's considered a branch, I still want to go in the order that comes closest to that functional group, or to that branch. And then we're going to do the same thing with the next compound. We're going to highlight. And again, if I start on either end here, if let's say I started backwards, when I get to this fork in the road, I have to decide which way to go, and I want to go whichever way is the longest. Okay, I could have also started from the left and went across, and I'm still going to keep going because that's the longer path. And then I want to number them in the order starting at the end that's closest to that branch. So here I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. So in both cases, my longest carbon chain goes up to 8 carbons. And on carbon number 3 is a CH3 group, is that methyl group. Okay, so these have to be the same compound. These have to be conformational isomers because they have the same carbon chain length, 8 long, and on the third carbon is that methyl group. So conformational. All right, second example. Again, we're going to start by figuring out those molecular formulas. So, Christmas tree it so that we have all the carbons. And then again, both, we've got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we know each one of these is starting off with a C5. And then to determine the number of hydrogens, you can take and turn them into condensed structures. So again, I'll just do that for the first one. You can do it for the second. We have a carbon, carbon, 3 carbons, and then an oxygen, and then 2 more carbons coming off of it. Again, I'm looking at this first structure. And then on that second carbon, we have a double bonded oxygen. Now I go in and fill the hydrogens in. The first carbon only has 1 bond, so it needs 3. The second carbon already has 4 bonds, so it doesn't need any. The third carbon needs 2. And then the fourth carbon also needs 2. And the last one needs 3. Okay, so if we add up all the hydrogens, you should get a total of 10. So we've got C5H10. And you'll find that that is the case for both of them. And we've got 2 oxygens. So O2. Okay, they both have the same number of each type of atom, so we know it's either conformational or structural. And the next question is how long is the longest carbon chain? Okay, so here I can find 3 carbons without having to pick up my pen. And on this side, I don't want to start here because that's only 1 carbon before I hit the oxygen. So I'm going to start on the other side, and there I get 4. So I can already tell that these are not the same compound because the first one is only 3 carbons long before I hit an oxygen. And the second one is 4 carbons long before I hit an oxygen. Okay, so they have the same molecular formula. They are isomers, but I can tell they're not the same compound, and so they have to be structural. All right, and last example. Again, we're going to start with the molecular formulas. So we're going to add our dots to count the number of carbons. Okay, the first structure, I see 1, 2, 3, 4, 5, 6, 7 dots. So we've got a C7. And then on the next one, if I count up all the dots, I've got 1, 2, 3, 4, 5, 6, 7, 8. I can already tell that they do not have the same molecular formula. And so instantly that's unrelated. Those are the easiest to spot. Okay. That is the end of the structural and conformational isomers. In the next section, we're going to look at cis versus trans. Okay, so we'll see if we can get through this pretty quick. So with cis versus trans, you are looking at either alkenes or cyclical structures. So cis is going to be on the same side. And with cyclical structures, that means that you're going to have what we call wedges or dashes. So here, this is what we call a wedge. And here is what we call a dash. So you would have to have either 2 wedges or 2 dashes in order for it to be considered on the same side. The wedge is sticking out at you in front of the screen, and the dash is sticking out behind the screen. So they're on the same side. And this is in front. But it's the fact that you have both wedges or both dashes that make it a cis. Now, with the alkenes, the easiest way to do this is that you're going to draw a dotted line straight through where that double bond is. And if the things coming off of the double bond are both on the same side of that dotted line, it's going to be cis. And so here another example, we're going to draw a dotted line through that double bond, and both structures are located on the same side of that double bond. Okay, so those are cis isomers. And then the other type that we've got are trans. So trans means the opposite side. Okay. Again, for a cyclical, trans means that you're going to have one wedge and one dash. So you've got to have a wedge and a dash. That means one is going in front of the screen here, that's the in front, and then one is going behind the screen. So they're on opposite sides of the screen, and so that's trans. With the double bond, we're going to do that same concept where we're going to take and draw a dotted line through the double bond, and this time the groups on either side of that double bond are on opposite sides of the dotted line. And we can try this again with the second example. Draw that dotted line through the double bond, and notice how they are on opposite sides of that dotted line in both cases. Whereas up here, for cis, they were all located on the same side of that double bond. Okay, so that is the difference between your cis and your trans isomers. So that wraps up our isomers, and then in the next section we'll talk about chirality.